Hey, John here. I just added a new directory to my Verilog examples that discusses the case Z, and case X. I'd like to thank you all very much for watching, subscribing, commenting, thumbs upping, and supporting my channel in other ways like Patreon, especially the VIPs shown here. So, first thing we're going to note is that these things, the case construct in Verilog is, or I'll say can be used very much like the switch statements in C, C++, Java, C#, and so on. But in Verilog, we have a lot more control over the exact number of bits that are being used in the expressions and the comparisons that are being made, and how to deal with things like, what happens when there's an unknown value in one of the bits. So here's my copy of the files we were just looking at from the repo, linked to below in the description on YouTube. Let's first clean this up in case I got a mess in there. Case 0 is the first one, and this will give us a kind of a big picture, broad view of what's going on. We'll walk through a bunch of examples. Hopefully we'll get the feel of the thing. And as you can see, then there's a case 1 example over here, which I was kind of surprised the first time I saw that. This is kind of using the case construct backwards. So yes, this is a separate little discussion we'll have near the end. Very useful when we're using case constructs in finite state machines, okay? So you want to see this before we dive in later on and get confused. So first things first, let's look at the case statement here. This is the exact same thing I discussed last time on YouTube, which is a 7-segment decoder for hexadecimal digits on an LED. Okay, and this is the exact same file. What I did is I came in here, and all I did is replace the if, else if, else if, else if that was in here with a case statement. And you can imagine if you've ever used a switch in languages like C and so on, this is going to look a lot like that, except you put the case up here instead of down there. A little, grammatic sugar. But you also have a little other things that we'll see that crop up here. All right, so first of all, you might recall what happens is I got a 4-bit binary value as an input to this module. I also have an enable signal, and I've kept it. This is the exact same as it was last time. So the 4-bit value on this D vector here will decide what bits, which LED segments you want to turn on your LED, and they're labeled A, B, C, D, E, F, G, like I said last time. You can go back in the playlist, again, link below this video on YouTube if you want to watch that one to find out, if you don't already know, what these letters mean and how they map to the 7 segments of an LED. Okay, so all this is the same, this is the same, and so on, all the way down to here, not a single change. Okay, what happens? How does this work? Well, you say case, then you put an expression in here. A Verilog calls that the case expression. And you take the value of this expression. In this case, it's just what is the value of D. Real simple, right? And then you compare the value of D to each of these case items, is the word that they use in the spec. The values are compared in order, starting in the first one. So if the value of the 4-bit D vector equals all zeros, then execute this statement over here, and so on down the line. Now, if you need to have more than one statement in here, you have to say begin and end around it, just like you do in the if statement, right? Now, we only have one statement in this if body, and that is the case itself. If we scroll down here, just like before, the else is to set all the output signals to Z's. Okay, so again, down here, nothing's changed, just everything from case to end case here, okay? So what do we do here? Let's say case has the value of 1 in binary or hex, right? So 1, it'll match this, say no, it'll compare it to this one, it'll say, oh yes it does, therefore it'll execute this and set the segments to these values. And anyone who's seen an LED 7-segment display before would know that the number 1 has 2 segments on and all the other ones are off, right? Because it looks like an 8, and the 2 segments on the right would be on. That would be these guys right here, okay? Obviously, if D was a, 0110, that would be a 6, and it would come down here after, checking these. No, it would be this one. So it would execute that and set it accordingly to this. And of course, a 6 this 6 would have a top on it and go all the way around like that. So all the LEDs would be on except for the one in the upper right corner. Okay, so you'd expect to see all ones and a single 0. In the case for the 8 here, this item, right, all of them are on, right? The 0 would be all of them on except for the center piece, so you should see one off in there for a 0 as well. Now, I listed these in numeric order, starting from 0 going up through F, because that seemed a natural way to do it. But we'll rearrange this as we go through this video to see what happens, because remember, order matters when it's logically, right, based on the definition of Verilog. If the value of D matches more than one of these, in which case, at the moment it can't, but if it did, the first one that it encounters along the way is the one it will use, and it'll execute that line. And that's the very important point here, okay, as we get more creative with these. It's the first match, okay? Now, we have every possible value in here, from 0, 0, 0, 0, which is that, all the way up to 1, 1, 1, 1 in hex, which is F. So I have other ones in here as well. What the heck are these about? Well, let's have a look-see here. Let's ignore this for a second. 0 through F are all matched in here. Now, during simulation, remember, the D value can have unknowns in it. It could also be high impedance. Those are Z's and X's. These are unknowns, right? And these are the, well, we'll talk about that in a minute. If it has Z's, it would be high impedance. But if these aren't here, what would it do? It would say, well, it doesn't match any of these. In simulation, that would be the case. And it would go down here and it would do the default. At which point I set all the output values to X. Now, I set all the outputs to X here in the default of the case so that it's observably different than what happens if I disable the LED. We talked about that last time. And I set it to all Z's. So these are unique output patterns, and I can recognize each one. Now, let's run it and then have a look, come back and look at what that's all about there. Okay, what do we got here? Here's your 0 through F, and these are all going to be, matching exactly. I at least printed this out in binary this time, so if you can't do these in your head super fast. Here's all the combinations from 0, 0, 0, 0, all the way up to 1, 1, 1, 1. 0 through 15 in decimal, 0 through F in hex. They're all enabled. This is the normal decoding patterns that you would expect to get out of an LED decoder, okay, for hex, right? Now, down here we see some other patterns. I guess it would be a good idea to have a look-see at the test bench. Okay, this is completely untouched all the way through here. In the for loop we talked about last time, this thing here is commented out. You can turn it on and then it'll draw the little pictures of the 7 segments. We saw that last time. So everything down to here is the same as it was before. Okay? Oops. What do we got down here? I print these asterisks, as you saw, and the output when I ran it. And then I tinkered around down here with adding some new patterns. I think even last time I had, the X's in here and Z's and stuff like that. But my point is I put some messy patterns in here. And I got cute. I set one of the bits of the vector to X and 0 and all that. Well, let's not worry about decoding the meaning of all this code in here. I'll leave that as a task to the viewer to walk through this code and see what's going on. The point of looking at it is to just get ourselves oriented. Because up here I have a monitor on all these values anyway. So if D ever changes its value, or any of the A, B, C, D, E, F, G's, or the enable, or anything, this monitor will fire and it'll just print out everything that's going on. And that's the useful part here. If we see the value of D in the output, we don't have to reverse engineer all this crud down here. Not that it's particularly difficult. I'm just saying it's a waste of time because I print it all out. And that's what you're looking at over here. All right? So what happens with the LED module when the enable is true and that thing goes into it? Well, the answer is it can't match any of the exact matches from 0 through F. So we have to start getting creative at the bottom of that case construct, and you'll notice this matches the default value. Remember I said the default was all X's? So these are all easily identifiable, right? If it's disabled, it would be Z's. If it doesn't match anything above, including these weirdo things here we'll talk about in a minute, then we'll get all X bits. So let's run it again. That's what we've got here, right? This doesn't match anything by exact match, so we got the default case, which is all X's. If it's disabled, we got all Z's, because that's what we get due to this else down here. We talked about that last time, okay? So we can basically ignore these ones here when we got enabled to 0. But what about this one here? We set it all to Z's. And we set it all to X's right here. And we get these funky patterns that you saw in the code. So let's have a look-see at those funky patterns. Well, we're dealing with a case. And the case, like the if, else, is an exact match. So if I put 4 X's in my case item here, and D is 4 X's, as was the case in this line down here, and I should see XOXOXOXO. Kisses and hugs, as it were. So, and that's what we've got. Now, it turns out that for whatever reason, the Z and the question mark are interpreted as the exact same value. So I could either use this or I can use that in my code when I'm doing these comparisons. All right? A lot of people prefer the question marks. Maybe they stand out better. I don't know. It's very common. You'll see these. So if you set it to all Z's, it will match these guys. It'll also match this thing. Either way it would work, okay? So that's why I print out the OZ, 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 OZ. I guess that one is the Sleepy Eyes version here. So if it's enabled, I got all Z's, it's going to match. Print out Z's. Disabled again is all Z's down here in this pattern, okay? Which is obviously different than the one here when it does match the all question marks or all Z's above. Now, as is the case up here, we also have some interesting things what happens when you mix these things. Now, in a case, it's an exact match. And this won't match exactly. Won't match, won't match, won't match. And in the cases where they don't match, I set them all to X's. So this is what we would expect to see. Now, if you click on case 0, yeah, there we go. I put some notes in here, okay? So let's go back and double check my notes. So you don't have to go back and review the video all over and over. So what happens in here, you can see that this is it won't match what takes the default. This is disabled. That one's disabled and so on, right? Now, these are also checking myself in case I misspeak. So let's look at case Z now, okay? Now the difference between case and case Z is absolutely nothing to the code other than this. Oops. All right? All I did is I changed case to case Z. Let's run it again. Now, let's look at this. Already you can see a difference up here, okay? The first one, okay. Again, these are exactly the same. So what's the difference between case and case Z? Well, case Z allows the Z values on the input bits in the D value and the case items when they're compared. It will allow that to be a wild card. So we're no longer exact matching. We're saying if there's a Z involved in a comparison. And I said that very carefully because you're going to find out it works both ways in a minute. If one of the bits is a Z or more in either the D value or the case item. So if there's a Z in here or there's Z's down here like there is in this situation there, those will be wild cards in the comparison. Okay? So maybe we'll comment some of these out and see what happens or rearrange them and stuff like that. But let's have a close see at what's happening first right out of the gate. If I say 1x11 in my D value here, Now remember last time, let's go back up here. 1x11 didn't match anything exactly, so it got the default case, which is all x's. Now a 1x11 does match the case where we had all z's in our case item. So let's go ahead and find led.v here. We can easily jump back and forth. So this doesn't change up here. You know that. Let's keep an eye on what's going on down here, okay? You just saw that it matched this thing down there, right? 0, 0, 0, 0. So the 1x11 value arriving in D does match the all wildcard case. And remember, these happen in order. So if this happens somewhere else in this sequence, you'd get different results. Not in this particular case, but if you put it first, then no matter what you sent in here, it would always match this wildcard case, all right? And we'll just run that for fun while I'm on it, because that's what I do. I like to ruin code in the middle of an example here. Okay, there we go. Let's run this one. All of them. Whoa. Oh, these are disabled, right? Because the if expression is a priority encoder. If it's disabled, that takes priority over anything else. So this should make sense at this point. Anything that ends up passing this enable test in here will match the all wildcards and go 0, 0, 0, 0 in any situation where you're using kz. And the first item is all wildcards, okay? So you can't ever match anything else. So order matters a lot, okay? So let's put this back down where it belongs. And, okay, there we go. LED, get an eyeball on the bottom stuff. Okay, so that, again, just proof that order matters, okay? And why does that match this and not anything else? Well, remember, X is not a wild card when you use case Z. We'll see in a minute. X is a wild card if you use case X. So depending on which one of these you use, spoiler alert, more of the possible values are wild cards than they are and when you're using the more specific ones. Like case has no wild cards, case Z has Z is a wild card, and so on. Okay? So if it's disabled, we're going to get the usual disabled values. This one's what again? Enabled. And now this is interesting. The value of D is all Z's. So this is, symmetric. I'll show you a note somebody posted on whatever it is, Stack Overflow, where they talk about this in some more detail. It's another discussion. There's a lot of discussion of this, by the way, all over the internet, and you're going to get millions of opinions. So if I don't touch on something that you don't quite get, Google around a little bit. There's a lot of this dialogues about this subject floating around on the internet. Okay, so in the case we were looking at there, we sent in the value of D was ZZZZ, and we saw the source code earlier. It might have been sent to question, because, like I said, the question marks and the Z's mean the same thing in Verilog. So if these have all wildcards in the value here, it'll match the first one it finds. If it has something else in here that doesn't match this and so on, like it has an X in it or something, it'll go chugging along until it sees this down here and say, oh, it matches this. It'd be very hard-pressed to ever get here. In fact, it's impossible in a case Z to ever get past this, because this will match anything, all right? So we should see no cases with all X's in that scenario. We look down the output here, and we don't. Up here, we do. So you can definitely see the difference between case X and case Z in these really simple examples here, okay? So what do we got? If the value in D is all wild cards, it'll match the first thing it finds, which is that, which is the 0. Remember, the 0 was all on except for the middle horizontal segment in the LED, which is G, which is the last one in the sequence of bits. So this makes sense. If it's disabled, even with the wild cards, of course, it's disabled. And what do we got here? If it's all X's, we're dealing with exact match, and only Z's are wild cards. And this does have an exact match to all X's in the case right here. And therefore, that should be the answer. And that is, we see it right there. If it's disabled, we go back to all Z's. If it's enabled, and I have a 10Z0 in the data. Okay, it gets interesting. What's going on there? Well, they're all on, so that must be the 8. In my note over here, it says matches with 1000, which is the first wildcard match that this thing will equal. And it's the first one because I list them in numeric order here. It matches this one, because 8 in binary is 1 followed by 3 zeros. The pattern we're trying to match is 1, 0, wildcard 0. Well, that'll only match 2 possible values. It'll be 1, 0, 0, 0, or it'll be 1, 0, 1, 0. So that's either 8 or A in hex, all right? So if we move A above the 8, again, order matters. Now, it'll equal A instead of 8. And you can see in this scenario right there, that's no longer an 8. That's an A, so that should be all but the bottom segment. And remember how the segments are lettered. The top one is A, the upper right is B, C, and D, therefore must be the bottom. So we got A, B, C, and D is a 0. So this is A. And we can double check that by looking at the source and just see what A is setting it to. And that's what you got right there. And it'll match because it found A in order before it found 8. I'll put these back in order, because if you do this, don't put these out of order unless you have a good reason to. And out of order, I mean numerically, because I'll just confuse just about anybody. So moving on to the next example, we got 10x0. And we're in a case Z where only Z is a wild card. So 10xo has to exactly match, or it could match all Z's in that case item. And that's what it does, because that's the value. And the all Z's are all question marks case item. It can't match this because X is not a wild card. It can't match any of these other ones because the X in the D is not a wild card, and it has to match these up here exactly. Otherwise, so that's not going to work. So we get the all Z's match. And if I go 1ZX1, there's another X in there that can't match anything. So it has to go to the all wildcard case item here to match the all Z's. Okay? Now, this is just an extension of that theme. Okay, case X means, okay, fine. Not only are Z wildcards, but X are also wildcards. We got lots of wildcards now. So we got this situation here, 1x11. What did it do up here? It matched the all Z's, because 1x11 does not match A through F exactly. XXXX, that item down here, it can't match this, because in case Z, or just case, that has to match exactly. And what do we got down here? In case X, where X is a wild card, we can match something else. That could match 1011, or it could match 1111. Whatever one it finds first, okay? Now, if it's all ones, it's an F. 1011 is what, a B? Well, let's see what's 00 all ones. That's a B. It's going to match that. Because we're going in order, right? It'll match the B before it chugs along to check and match the F, all right? So that makes sense. Or disabled, so these are the disabled cases. If we put in all Z's, that's a wild card. So it should match the very first thing that it finds, and anything would match, right? And that's the 0 case. We talked about that before. We're disabled here. It's all X's now. And X is also a wild card. So that too will match the very first thing it finds, which is a 0. Okay? Now that one is different, obviously, than up here, because this one didn't have a chance to match case 0, because X in this scenario here was not a wild card. It had to go all the way down until it found the case item, where the item itself was either a wild card or it could match this. Which one was it that I was looking at? The all X's version? Yeah, it would be that one there. Okay. Okay. So this case, it's all wild cards because we have a case X, and therefore it'll match the first case it finds with 0. Okay? Again, we got another disabled. Now we got 1, 0, Z, 0. And because both X's and Z's are wild cards, this would match the first one it finds, which would be the 8. Not the A, because the 8 comes first in order. That's definitely an 8. And X is also a wild card in case X. And the D as well as the case item, so that's also going to find the first thing, which would be an 8. And a 1ZX1 in order would probably be 1001. And my note down here to myself, that is the one it finds. So what is that? That's a 9. And an 8, difference between an 8 and a 9 would be that the lower left segment would be off. So in the 8, right, you got the top, down the side here, the bottom left would be off, then the upper left would be on, and this middle piece would be on. So that you got the A, B, C, D would be on, and then E over here is the one that's off. So you got A, B, oops, I've got to highlight one of these things, right? B, C, it's wanting me to drag it, D, and there's your E is off. So that's a 9. Okay? So more wild cards, less wild cards. In a lot of ways, not a big deal. But you got to keep in mind, and this is really difficult for me when I first looked at this stuff, very confusing, the fact that the data itself in the case expression here can have wildcards in here. I found it more, it seemed more common-sensy that the data would be taken literal and you would use these to express your wildcards. But this one goes both ways because there could be wildcard bits in D, there could be wildcard bits in these case item expressions down here, anywhere could go. So this can be kind of confusing, especially when you're using a case X when you've got X and Z both being wildcards. All right, so that you definitely need to keep that going in your head. Now, when I write Verilog, I use case pretty much no matter what, unless I need a wild card of some kind to simplify my code. We'll definitely look at that more closely later on, but that's when I use a case Z to get rid of all the extra cases, I don't use case X because, and that's actually mentioned in these notes down here, we'll come back to case X in a minute. So what is it? This note down here that I stole off of Stack Overflow here, a lot of people have this opinion. Just don't use case X because it really is the same thing as a case Z. How many wildcards do you really need kind of attitude, all right? Come back to that in a minute. So what do we do here? What do we know? The wildcard matches in these examples just happen to match against 0 in the case items. This is probably not as clear as it could be. What I should have said is something along the lines of, where's the edit for this darn thing? Let's fix it while we're here. Summary of differences, blah, 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 wildcard matches, and of data in D in these examples, I should say. Something along those lines. Let's go ahead and commit this. Because we're talking, this refers to what happens with the bits in D are wildcards, okay? In other words, these Z's or the X's in the case Z and the case X. They just happen to match against 0, okay? And that's what it's referring to. In the case items, I probably should have highlighted that as well to note that I'm specifically talking about these. This one in particular, these are the items down here, right? Magic is 0 in the case items, okay? This is only because the order of the items in the source code are in ascending order where I happen to put 0 first. And we saw if we rearrange them, we can get different results when we're using case X and case Z because it really matters, right? When there's wildcards, all right. So, what do we got? Because a synthesized circuit can never have an unknown value. I mean, think about it, right? You make a circuit, you synthesize it, it's real. There's either electrons piling up, a voltage present, a current flow, or there is not. You can't say, oh, I don't know, when it's real. So it turns out the idea of X, the unknown, is really a simulation sort of a thing. It doesn't really manifest itself in a real circuit. Yeah, you could argue, but if it's an illegal value, an analog value between the 0 and the 1, and well, that's unknown. Well, that's not how this really works, because digital inputs will settle that thing down to either a 1 or a 0 and commit either way, even if voltage is illegal or invalid, right? So, point is, because you can't really have an ax on an input value, you can have a don't care and an input or an output, but you can't really have a truly unknown value, okay? Because you can't do that. I tend to avoid using the case X, because what happens is it's not going to give you any more than you get out of case Z. Okay, and down here, as I say, when simulation can have these X values, when the simulation can't know because you didn't set it to anything. As a debugging aid, simulation tells you, I don't yet know. You have not yet specified the value of some bit somewhere. So it'll assign the value of X to such a variable. Okay. In that particular case, it would be nice to be able to match against an X, in my opinion. So I write a test case, and I'm purposely sending in an unknown value, like I do up here when I have like a disabled circuit, or it falls into a case where I assign an X to the outputs, and I want to match against that in a test bench. Now, I'm not going to use a case X because I won't be able to match a known value against an X. I won't be able to ask, does that equal this specifically? Okay? So I reserve the X's, as does apparently many, many other people. The vast majority of all programmers of Verilog tend to avoid using the case X because of this and or other reasons. Okay? Now, I've also read a paper, by the way, that argues that during synthesis, right, when you make a real circuit, if you use case Z and or case X, the circuit itself generated by the Verilog synthesis tools shall be identical. And we've sort of gotten hints and glimpses at this in the past, because I can't punch enough that Verilog was designed for simulation, and later on they discovered it's useful to synthesize circuits directly from it for specific types of subset of features of Verilog. Okay? And they just kind of made the rest work when it can. Your tool will also generate errors and say, I can't synthesize this if you design a circuit that just can't be done. Okay? In this particular case, I believe that I support the paper that I saw where it says, during synthesis, whether you see a case X or case Z, the circuit will do the same thing. Okay? Another reason not to waste time with it. All right? So during simulation, it can be very useful, in my opinion, to avoid using case X unless you really, really know what you're doing and you want to use it. Then just don't. Because what I said, sometimes you want to actually ask, does D equal XXXX, not just simply say, oh, D could be anything and it's a wildcard match. Okay? Think about it. All right, so here's this thing from Stack Overflow. What do we got here? Somebody asked, what's the difference between case X and case Z? And they gave a little bit of an example code, and in their code, the inster variable, as I recall, was the value that I put in. It was the case expression in a simple case, sort of like this. And so he's referring to the case expression. I should probably update this a little bit, but I don't want to misquote this person. Click here to see more details if you want to. The bottom line is, what does this guy say? A key difference between the expression contains X or Z values. When the case expression contains X or Z, that is the case expression, not the case item they're referring to here. Remember that both case X and case Z look at both the item and the expression when it's doing its comparisons, and this is where the symmetric comparison word comes up that I remembered reading somewhere. It's in the thing that I pasted right here. How handy. So we call this symmetric comparison because the don't care values can come from either the case expression or the case item. Okay? So they say if instr, the D, was all X's, none of the items in case Z would match in their example, because their example doesn't have an all X's item. Mine does. But all of the items in the case X would match. And the simulator would simply pick the first item, just like we saw up here. If I pass D equals all X's, and it's enabled in my scenario, it finds the very first item, which was the 0. Okay? So they're basically confirming what I just said, or vice versa, depending on who stole what from whom, right? Okay, so similarly, if it was all Z's, then all the items would match. I consider the case X a useless construct because, why bother? Like I said earlier, system Verilog. Now, this is kind of an interesting note. What happens in the next generation, right? And remember also that system Verilog is a formal superset of Verilog. I'm not talking about system Verilog because I don't have a lot of experience with it. I dabble with it sometimes. It has some nice features like this. If you really want your case construct to be able to have wildcards in it, but you don't want the data in the case expression here to be considered in this weirdo symmetric kind of comparison, where if D in my scenario had X's and Z's in it and make it wildcard match all the case items, you can put this case inside thing in here, as if that word means something to me. I don't know why they chose that word, but what happens is it turns it into this asymmetric comparison, which uses this bugger, which must be a system Verilogism. I've never seen that before myself, but it treats only the X and Z in the item as a don't care, which I honestly think is more intuitive. It's what I thought this thing did back a decade ago or whenever it was. Ooh, I'm old. Whenever it was that I first tried to learn Verilog, okay? Short of it is, if you want, you can use a different type of case if you want to upgrade to system Verilog, where the wildcards are only in your case items down here. These buggers here would apply, but as that guy says, the wildcards in here will not be treated as wildcards. Okay? If you want to go that route, knock yourself out. Okay, so this is the basic gist. I like to think of it as like, it's not the same as, but it's like the switch statement in C, C++, and so on. But we have this wildcard stuff going on, and because Verilog has these 4 state values for their bits instead of 2, it's not binary. Remember, this is the 4, I guess, quadrary values, the 0, 1, X, and Z values that can be assigned to the bits in Verilog, all right? So you have special support to deal with this wildcarding and the handling of those extra possible values, all right? Now let's look at case 1. Now, if you think this wildcard stuff is weird, let's look at this backward example. This one really blew my mind the first time I saw it. Now, remember when I said I chose my words carefully? This is why. Let's look at this situation. We put a constant in here. And we put variables down here. So, I had to do like a triple take first time I saw one of these. This is weird, okay? But if you think about it, I mean, logically, you can sort this out. What you're asking here is, does A equal a 1? If so, do this. If not, does B equal a 1? If so, do this. Does C equal a 1? If so, do this, and so on. Does D equal a 1? If so, do this. This is a priority encoder. No matter what B, C, and D are, If A is a 1, you nail it right here and you're done. No matter what C and D are, if A is a 0 and B is a 1, you're going to do this. Okay? So this is a priority encoder with a default down here. So if they're all zeros or some weird illegal thing, or they got X's and stuff, because remember, this is a case. I didn't put a case Z or case X in here. This is one way to make a priority encoder. There's other ways to do it too that I alluded to earlier. We'll have a look-see at those later on using wildcards. But this is an interesting way to do this because if you think about it, the actual circuitry to build this is easier, simpler than if you created a 4-bit comparison and you said, like A, B, C, D and curly braces up here, and then had all zeros and 1, 0, and so on to match these things. There's a lot more circuitry to build such a thing. Again, think about it. I'll leave it a task to the viewer. This one clearly only has to compare 2 bits in order to answer this question. And not only that, this is a constant. So you can use a single gate to answer this question, right? This is simpler than comparing A, B, C, D to a 4-bit value, right? Okay, so this is simpler, less gates, less circuitry. But it might take a little minute or two to think about what's going on in here. And it also might take a little bit of thinking about when it would be okay to do this. All right? Now, this will only be useful, in my opinion, if one and only one of A, B, C, and D are on at any given time. That's what we call a one-hot case, where only one of these is hot, one of them at a time. If more than one on it comes on at the same time, well, you'll get an answer, but it will operate as a priority decoder in that case. Okay, or priority encoder in this case, where it'll first check A, B, C, and D, and so on, right? Now, a one-hot case is rarely useful because it saves circuitry. In certain designs, you'll see them used in state machines, finite state machines, all the time because they use less circuitry, period. But it really depends on the applicability of it, to the specific application you're building. So I wanted you to see this because we'll bounce into this again. And there are papers written about this around the internet as well. In fact, if you go to my examples repo, there should be a link to my documentation, blah, 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 Verilog notes right here. This is one of these Cliff's notes I mentioned earlier in this series. Yada, 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 non-blocking, full case, parallel case. Is that where we see it? Because that's another kind of thing that happens with case constructs. And I don't know, nowadays you go to a website that's not HTTPS and everyone complains about security, I guess. Anyway, these papers are pretty good. If you look at this thing, you'll see, in fact, he talks a little bit case Z and case X, a little more dialogue, but this is not about case Z and case X. It's about full and parallel cases, more issues that can come up with your various tools. So he's talking about synopsis in particular. I'm jumping all over the place. I'm sorry, but I'm just saying you might want to eyeball these papers because there could be more to this than meets the eye, is my point. What do we got going on here? He's got another one. Oh, here's your priority encoder done with wildcards. Okay, so there's another way. This is the other way to do it. And like I said, you'll come into these. I strongly urge you to wander through and look at these papers if you're just getting started with this, because you should know about these terminology and know what it does. I mean, we'll be here forever if I have a whole videos on each one of these topics. You definitely are expected to be able to read if you watch my channel. Or you're in deep doo-doo. We're here because of this parallel case stuff and full case. And what you should understand, at least at this point, just by me telling you that a full case is a case statement where all possibilities are enumerated in all of the items, okay? And the reason that a full case is of interest is because the synthesizer can know that it doesn't have to worry about all these weird variations and infer latches. Okay? Because if you don't have them all in here and you're going to assign a value to Q like this, and you may not have a default either, what is it going to do? Okay? If you say full case, then and by the way, it'll be a tool, a synthesis specific flag that you put over here. Quite often you'll put something like this. Nowadays, you put something like this. I think that's how you would do it. Or you put an underscore in here. You'll have to look up in the notes to know for sure, okay? Or it has to go to the right of this thing. I think it can go right there. And you're telling the synthesizer that this is supposed to have entries in it for every possible match. And you're also saying, by the way, if I leave one out, create one in it anyway. Okay? And this paper talks about why you don't want to be gratuitous about this. Okay, let the synthesizer do its work. I'm going to throw that away. I don't use them myself. The reason you're going to see about them, the reason you're going to hear about them is because if it is a full case, then a simple multiplexer or a decoder can be used to build this circuit. So you're giving more instructions to the synthesis tools as to how you want it to do this. All right? So you got to keep in mind at all times what the circuitry looks like that you're asking the synthesizer to create. All right? I think that's like, it's when you're writing assembly language and you're using it at a very low level and you're keeping the machine language in mind at all time. When you don't have to when you're writing assembler, but sometimes you do, depending on how much, how close to the machine you really want to be. Well, in this case, no pun intended, if you're going to tell it you want a full case, you're like thinking about that machine code. The analogy here is that you're thinking about the machine itself, how the gates are going to be created from the synthesizer. All right? And when you deal with parallel case, that also is a hint. Actually, the parallel case is a direct hint that it should be using a multiplexer and or decoder to build this thing. The full case is a directive that says, if I didn't put them all in here, generate them anyway, so that you can treat this as a full case with no inferred latches and use a simple multiplexer and decoder. Again, diagram this thing out in gates and convince it yourself. All the talking I could do in the world won't help you if you don't really draw this up and look at it over. All right? I cannot stress enough that you should do that and convince yourself that works the way I just said. Or put some comments in YouTube below, please, if I'm wrong. If you get stuck, this is actually probably not the paper you want to be looking at. There's another one in here in the Cliff Notes series where he talks about case statements over the years. For like 20 years, he's been posting these notes. And he gets like, best paper at the, whatever, DevCon and HDLCon, these annual conferences and stuff like that. That are recommendations. You should do this and not that, and so on. You can see a lot of Verilog and some system Verilog stuff in here. Here's a finite state machine. In fact, this paper, I think, has an example, a really creative example on how to use what we just saw, by the way, in here. So you went on a board at some conference, blah, 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 and you look at these states. We'll talk about this much more closely down the road. And he's got a state diagram or a piece of code in here. Why is one always blocked, more verbose than three always blocked? Oh, yeah, there's a lot of details in here. This may take some reading. But when you look at these code, boy, that must be a newer version of the same paper when was that? Oh, that's 2019. Yeah, I must have read an older one. I linked on this one. Blind fail, no best practices for this. More system Verilog stuff. These are all 2014s. Here we go. There's the one that I had a link to before, two-state simulation. Actually, I think I was looking at this one. I don't know. I'm gonna have to get it. I'm gonna have to go back through all my notes here. Never call an audible on YouTube. It was a shorter paper than the one we were just flipping through. This one is 50 sheets. Yeah. Oh, there you go. So here's one hot coding style. So you're gonna run into this when you see things posted to the internet. Now here you got this really interesting variation of, here you go. Here's your one hot style case construct. And he actually has a vector of bits with these things specified as parameters. This is bad. This is an older paper. You got to be careful. This one is from like, wow, this is oldie-timey, 2003. So you got to be careful. If he wrote this today, this would be a local parameter. Maybe they didn't have them in Verilog 95 or something like that. You also see the word or in here. That's the same as putting a comma. In the oldie-timey days, we had to use the word or in here, which I never liked at all. This is difficult on my eyes. I would have much rather said pause clock or clock, comma, neg edge reset n, and so on like that. But this is a variation of what we just saw, which is really what I wanted you to see. And he's actually got a vector of bits in here that has these indices into them. This is his 4 bits of state here. Okay. Now this is a state machine, but my point is we'll look at this next time. This is one of these things where you have a constant here, and you have your 4 different bits. He simply expressed it, though, as elements in a vector. And then he's also setting the next state of his state machine in the items here. But this is a lot to take on at once when all you're trying to do is understand what a case is, and you're going to look at it in the notation that we have right here, which is this thing. So I boiled that example down to this. If you want to work ahead, look at the 2 next to each other and see that we're really talking about the same thing here. And he also has other things involved in that app because he's created a finite state machine. Now let's look at the test bench for this before we go, and then we're on our way for another weekend. Okay, so what do I got here? I got a 2-bit output from my unit under test, and I got 4 bits of inputs going into it. Now, I named these on purpose differently than each of the keyword parameters here, just because I didn't use a really good example of that last time I named them both the same thing. So I wanted you to see an example before we get too far along where these are the variables in scope of the module here, of the TB module, right? These up here. And these are in the scope of the module being created, all right? And what do we got here? We got a monitor on all the values, and then we just simply set them to a bunch of different things. We got a 1, 000, 0100. These are the cases that are the normal ones. The legal, proper, and correct one hot cases for that case construct. And then these down here are values that would normally not be legal if you were going to use that case construct, the one hot style case, in an application. These would be the weirdo values, all right? And remember, I used case, not case Z, not case X. So these are just wrong, all right? But let's go ahead and chuck it in there and see what happens. You know, what happens if I do this? What happens if I do this, okay? And that's what you need to do when you're just getting started and learning stuff here, okay? So what happens here? If A is on, we got a 0. If B is on, we got a 1. If C is on, we got a 1, 0. And D is on, we got this. So those are the normal one hot cases, all right? Now, what if none of them are on? We fall into the default. Okay, let's go ahead and look at the code again. Right there. Okay, if none set, it can't match anything, so out got set to double X right there, okay? What if I got a 1010, which is weird, but you can use this construct as it is for priority encoding. If you have like I said, if I have 4 interrupt bits coming into a CPU and the one on the left has higher priority than the rest, and so on as you go over to the right, well, which one should be processed if that's what the CPU sees right now? Well, this one being A, which is 0, that's their high priority. So there's one way to do a prioritized interrupt recognizer. Okay. What else do we got here? We got all X's. What does that do? Case, exact match. Does any of these equal X? No, so we do the default. They're all Z's. Exact match, nothing can match. We got this. Now it gets interesting. Remember, A, B, C, and D are single-bit wires. This is really why I wanted you to look at this thing. Look what happens. We're comparing a single bit in each one of these case items. In the previous example, we looked at the D value, which was all 4 bits together. Now we're not doing that. You might argue, how can this be? How can I get a 1, 0 out of this thing? I don't have a case X or a case Z down here, and I don't have any wild cards. You're not following along, okay? If that's the case, this is A, B, C, and D. So we're asking, does A equal 1? No, it's an X. Does B equal 1? No, it's an X. Does C equal 1? Yes. And we're asking that question 1 bit at a time exclusively. So just because I printed them out together, and I might think of them together, they aren't together. And they're not compared as a group in any way. So if you're thinking this way and you're building something this way, but you're using a case construct, this is actually why I removed the square brackets. Because I was thinking about putting Cliff's, one of Cliff's examples in here. He's got these show up in a couple of different papers. He has one that's relatively simple like this. And I decided to go with explicit wires instead of creating a vector. That just adds too much to think about when you're first learning. Because you really need to understand that this is not a wild card kind of a search. Okay? So that's why C is the one it matches right here. And this one here, it'll match B. Same thing. Doesn't match any Z's, but it looks like B is good when it gets to here. Is B a 1? Yes. Don't care about anything else. That's my output. Okay? So these are like great fodder for student quizzes in college. Here's a bunch of stuff. What'll it output if I put this in there? And so on. And ask them if they can figure it out. And not give them access to the internet when they're answering. Because you should be able to do this once you've kind of given this any real thought. Okay? So that touches on a lot of the things I want to make sure everybody has seen and has a chance to take in a little bit before we start trying to apply these various case constructs to things that we design, like finite state machines and other circuitry. All right? So let me know what you think in the comments below. I always appreciate comments. I've always read all the comments, by the way, on my channel. I don't get that many that I can't keep up with them. And some people have really excellent ideas, and when I'm wrong, by the way, if you click on the description below the video on YouTube, I will list I made mistakes here, there, and the other thing, and this is the guy that pointed it out, and you can see that in the comments as well. So I find them very useful. So if I blow it, please point it out. No hard feelings here. We are all trying to learn stuff at all times. No one's a genius. We're all figuring out as we go. So, till next time, thanks for watching. I'm John Winans. See you on the internet.